our third speaker, Wai Lun from University of Palace.
Thank you, Professor Lam, for moderating the Q&A sessions. Right now, I will pass on the stage to Wai Lun for his presentation.
Okay, a very good afternoon, ladies and gentlemen. My name is Wai Lun from Palace University, and today I'm here to share with you my presentation on the potential of glycerin pitch in mixed cultured polyhydroxyalkanoate production, component characterizations, and organic loading rate optimization. So to begin, the research background relates to the theme of responsible production in the palm oil related sectors, specifically in the oleochemical industry, where our main focus is on the resource recovery from glycerin pitch. So in a typical oleochemical plant, crude palm oil is used in the transesterification process to produce fatty acid methyl esters. One of the main byproducts of the transesterification process is known as crude glycerol, which is typically purified to produce refined glycerin to be sold off to other industries. However, one of the main scheduled waste produced from glycerol purification is known as glycerin pitch, or GP, that is conventionally managed through either incineration or sealing in drums prior to landfilling. Now, incineration not only produces toxic aldehydes such as ethylene, but also produces 2.5 times more of carbon dioxide gas that pollutes the environment as compared to the incineration of coal. Additionally, landfilling may also risk soil pollution due to the presence of highly organic compounds that are in GP. These negative environmental impact sparked various researchers to focus on the resource recovery of glycerin pitch, including using GP as liquid biofertilizers and as binders for eco-roof tiles. However, one of the more interesting resource recovery studies have shown that GP can be used for bioplastic production such as polyhydroxyalkanoate, or PHA. Now, PHA is a biodegradable and non-toxic biopolymer that is accumulated by some microorganisms when there is carbon source. It has a wide range of applications such as bioplastics and biodegradable food packaging, and that it is essential in addressing the existing single-use plastic waste that we are facing in the world globally right now. Moving on to the problem statement, there are currently limited studies conducted on the PHA production using GP. First of all, Yatin et al. Research on the PHA production using GP and a pure culture, only to report poor PHA yield of 5 weight percentage. On the other hand, Ramachandran and Amirul researched PHA production using GP as well, but using another pure culture, but now with the addition of co-substrate of 1,4-BDO, only to improve the PHA yield to 36 weight percentage. The limitations of these two studies include that there are low PHA yields reported and that they only use pure culture. Therefore, one of the potential alternatives that could address this limitation would be to conduct PHA production using mixed culture instead, which has added benefits such as lower production costs, wider range of substrate consumption, and higher tolerance to toxicant as compared to pure cultures. However, there are currently no studies that have been doing this at all, which is why an ongoing study is conducted to investigate the feasibility of GP as the waste substrate in mixed culture polyhydroxyalkanoate production. So in this study, a cultivation reactor is first set up, operating under the aerobic dynamic feeding strategy using the activated sludge collected from Inga Water Consortium as the inoculant. Then, GP that is collected from KLK oleo is used as the waste substrate at an organic loading rate of 500 mg carbon per liter day. Nutrients are also fed to the reactor to support biomass growth. So what we found is that from the reactor, steady state is achieved after 12 weeks of operation, where a stable culture is successfully cultivated using GP as the substrate. Then the enriched culture is sent to a separate accumulation reactor with a higher GP concentration of 700 milligram carbon per liter day to maximize PHA production. So from the accumulation reactor, we found that 80% of the organic compounds, 80% of the organic compounds in GP are degraded by the enriched culture. However, we found out that there's low PHA yields of 3.51% reported only. Interestingly, however, we found that there's unusually high increments of biomass concentrations detected, which can point to the hypothesis that other storage products than PHA may be produced. Which brings us to the proposed research objective of this follow-up research, where we, number one, aim to characterize the storage products produced, identify the dominant microorganisms in the enriched culture, and to optimize GP organic loading rate in the culture enrichment reactor. So moving on to the research methodology, the first objective is completed by taking sludge samples from the accumulation reactor and subjecting it to characterization. Existing characterizations include DOC, PHA, glycerol, and methanol concentrations. Through literature review, we found out that the other potential products that can be produced include glycogen, triacylglycerides, lipids such as biosurfactants, as well as extracellular polymerase substances or EPS. Therefore, additional characterizations on these components will be conducted as tabulated over here. Moving on to the second objective. The second objective is achieved by taking the sludge samples from the accumulation reactor and sending it for genomic DNA extraction using standard lab procedures. Pure DNA samples are then sequenced through high-throughput DNA sequencing instruments such as Illumina, followed by genetic code documentation and quantification. Through these data that we obtain, bioinformatics analysis can be conducted using the heat map as shown as example over here that allows further detailed analysis on the bacterial metabolic function, growth condition, substrate preferences, and storage product accumulation, which are key information necessary for our next objective on to optimize the culture enrichment reactor operating condition. Now, the third objective, OLR optimization, is necessary because, number one, we want to maximize the storage products that are accumulated by the microorganisms. Number two, we want to reduce the extent of dilution necessary, which hence leads to higher utilization rates of GP. Finally, it provides key insights necessary for future process industrialization. So the optimization study will be conducted using the modified activated sludge model 3, ASM3, as proposed by Fang et al. That contains 7 components and 5 processes. A general procedure of the optimization study is that number one, ASM3 will be set for sensitivity and collinearity analysis to identify sensitive parameters and correlations between the parameters in ASM3. This is followed by model calibration using experimental data to estimate the sensitive model parameters identified in the first step. Then, the calibrated model is used for simulations at higher OLRs to predict the PHA accumulation performance at higher OLR without conducting any experiments. Moving on to the research impact, this research is expected to impact the palm oil sector by reducing the dependency of conventional GP management methods such as incineration and landfilling, which directly reduces the amount of echolin and CO2 released to the environment and hence reduce the risk of soil pollution as a result of landfilling. Additionally, this study also promotes the establishment of a circular economy in the palm oil sector where GP is rerouted for resource recovery instead of disposal, which can contribute positively to the palm oil sector through the generation of value-added products such as PHA and the reduction of waste management costs due to incineration and landfilling. Additionally, as the mixed culture used in this study is activated sludge that originates from the wastewater treatment sector, this study promotes cross-industry synergy and cooperation between the palm oil and wastewater treatment sector, which can lead to lesser waste and the generation of more value-added product for both sectors. Finally, as this is the first ever paper to study on the bioconversion of GP to PHA using mixed culture, This research acts as a breakthrough study that can help future researchers to focus on further optimization studies that can then focus to maximize the production of value-added products and future industrialization. Moving on to the research timeline and plan, this Gantt chart shows the proposed research where important milestones will include the completion of DNA extraction, DNA sequencing analysis, optimization of the culture enrichment reactor, as well as publication plans, which includes the POPSIG newsletter article, paper submission to JOPE, and the presentation of findings in the POPSIG evening talk or webinar as tabulated over here. These are the references used in this slide, and I would like to present to you the supervisory committee of the research. Dr. Yun Li Wan is the main supervisor, who is also present over here. Dr. Evelyn from UM and Dr. Low from Taylor's University. Thank you very much for your time, and I look forward to your suggestions and advice.